assuming I simplified it, but we'll see later on. Okay. That is just to say hi, and you don't need my video, so let's go to sharing my screen. Okay, everybody see my screen? Yes, no, maybe?
Yes.
Okay. So this is just what we covered yesterday. We looked at the climate of a location, how to describe the climate of a given location in terms of spatial aspects of it and the temporal aspects of it. That's what we did first. And then we looked at the factors that determine the climate of a location. We went through the global factors yesterday. Somebody raising hand. Let's see. What do we have here? What? Gilbert, you want to say something? Or is it just by accident? Gilbert, maybe it's by accident. Somebody raised their hand, so I think that's why. Okay. Okay, anyway, so we say there are both global and local factors that determine what a climate of a location might look like or might feel like. And the global factors, we looked at the energy balance. So the energy coming to the surface at the equator is different from that at the poles and in between. And we said based on that, we divide the Earth on different circles from equator, the tropical of Cancer and Capricorn, then the Arctic Circle. And this energy balance leads to this thing called global climate zones, which I said, like I said yesterday, based only on the energy that the surface receives. So a lot of energy in and around equator, and then energy decreases. And I said this energy difference, the difference in energy between the equator and the pole is one of the main things that drives the climate of Earth's climate totally. And then we talked about how the difference between this one and this one, and the fact that the previous one is just energy, and this one is actually rainfall and temperature. And yesterday we saw that for Africa, actually rainfall plays a prominent role in this classification. Then we talked about Earth's rotation around the sun and how that leads to an apparent movement of the sun, north-south movement of the sun on Earth, and how with that apparent movement of the sun between 23.5 north and 23.5 south, how that movement determines the season, and how certain areas could have single rainy season and some areas close to the equator could have two rainy seasons. And then I think we looked at this, how temperature and rainfall progress with the seasons. So the seasonality aspect of things, this area is Zambia having one season, and Kenya having two seasons because of proximity to the equator. This is what we covered. We also looked at this one in terms of this what we call zonal circulation on the earth, and where air rises, leading to rainfall, and where it sinks, it leads to dryness. So this overall, and that sometimes this shifts, and the shift results in disruption in rainfall over different parts of the globe. So today, that was yesterday, today we will look at local factors. And so uh, if you just look at the global factors, the global factors may not give you this climate. So this cannot give you only global factors uh, because the global factor, there is no big difference in terms of global factors, let's say between Ethiopia and Sudan, like close nearby areas between Ethiopia and Sudan. So there are, even in Kenya, there are different parts of Kenya will have different climate, just even not far apart, like 100 kilometers or 200 kilometers apart, locations in Kenya will have a different climate. So, but that is not because of the global factors. The global factors are almost the same, yeah, with for areas around, at least around the same latitude. So then we're saying now it is must be the local factors that modify what we get or what we're supposed to get from the global factors. One of those is orography. Orography plays a very significant role in many parts of Africa, in many parts of the world. So that is one thing. I think we'll come to orography later on or more detail. Another one is albedo. Albedo means how much energy a surface can reflect. So you can interpret albedo as reflection of energy. So on a given day, if you have a grass versus an asphalt, you will see which one absorbs a lot of energy, which one reflects spark. So that affects, so the temperature in a town or a city is different from the temperature outside the city. It's because of one of the factors, the surface, in terms of how much energy is reflected or absorbed and how much the surface heats back. So, usually cities are called heat islands because they will be warmer than the surrounding because of the surface, the built environment in the cities. So you cannot use the temperature in the middle of the city to infer the temperature on a farm outside the city because they will be different, even similar. If everything being the same, they will be different only because of the different land use types. The other one is, of course, proximity to a water surface, either a lake or a sea or an ocean, that also modifies the local climate. This issue of idea of sea breeze and land breeze. Okay. So sometimes it will be cooler near the water body because of the wind coming from the water body. So that modifies. Also, even in certain areas, it also can modify the rainfall because of the evaporation from the lake. Like places like Lake Victoria in Africa, they have their own local climate, which is different from the other areas, only because of the lake. And of course, and vegetation plays a significant role in terms of, again, modifying or moderating climate. Maybe that's why for people coming from Ethiopia, the country is claiming they've been planting what, billions of trees over the last 4 or 5 years. But eventually we might be able to see the effect if those trees grow. So anyway, the effect, they do play a significant role. Number one, they can slow down the wind, which could lead to increased rainfall. Of course, the evapotranspiration from those trees can provide more moisture. So there are a lot of roles, different kind of roles. The vegetation can play. Of course, I mean, if you compare a city with trees and a city without trees, you will notice that the city with trees will be cooler than the city without the trees. I mean, assuming substantial coverage of the trees. So anyway, so those all um, can moderate the climate. Whatever we get from the global factors, these local factors play a moderation or a modifying role. So now I want to talk more about orography, which means the effect of mountains or mountain ranges on rainfall, because like I said, it is a significant factor. So before we go there, how it's good to understand how, just to review how rainfall forms. Rainfall, for a rainfall to form, we need two main things. Number one, we need a moisture. And normally that moisture comes in the form of a water vapor. And that water vapor normally comes from somewhere. So moisture availability is the main thing. Locally, like when you have like areas like Lake Victoria, can provide local moisture, but it is in many cases, the moisture is transported from the oceans. So for Africa, the moisture comes from Atlantic Ocean, from Indian Ocean mainly. So the moisture comes and provides rainfall for different parts of the continent. Now, once you have the moisture, moisture is the vapor, right? I mean, it comes in the form of a vapor, but rainfall is liquid. So that moisture has to cool down and become rainfall drop, right? So for that to happen, I mean, for cooling, it has to rise. So ascent is very important because the temperature decreases as we go up. Okay, temperature as you go up, temperature decreases, and so when the air with the moisture rises up, it starts cooling down, and then the water vapor will condense into small droplets, and those droplets come together and become raindrop and come down as a rain. Now, one question about a simple question about rising about the the decrease in temperature as we go up. So here is a question you can think about. As we go up, so we said the source of energy is the sun, right? So sun is the source of energy. But as you go up, you'll be going uh, you will be near the source of the energy, the sun. For example, at the top of Mount Kilimanjaro is closer to the sun than maybe down in Mombasa. Yes, Mount Kilimanjaro, Mount Kenya, the top will be close to the sun than a place in coastal Mombasa, but still coastal Mombasa is much warmer than top of Mount Kilimanjaro. It's the same when we fly with on the plane. Even though the plane is close to the sun, it is inside is cold actually. I mean, it is because heated. Otherwise, if you can step out of the plane at that level, you will freeze. So why is that? If the energy is the sun, why is the temperature decreasing with height? Why it's decreasing as we get closer to the sun? So that's a question for you to think about. You can answer later on or not. Okay, so let's go to now the effect of orography. So remember we said for the cloud, for the vapor, the moisture to become rain, it has to rise and give you rainfall. It has to rise, so cool down. So, and turn into water droplet and then give you the rainfall. For that to happen, there must be something pushing that moisture up. Okay, so there are many mechanisms that pushes moist air up. Number one, it is what we call buoyancy, because if air is warm air always rises. So just simple buoyancy, so heating and surface heating. When surface heats, air becomes warm, warmer air becomes lighter, and lighter air always rises. That is the thing. So that's one aspect, what we call convection air. Warm air rises, as it rises, it cools down, and then gives you rainfall. That is what happens at a local level. The other way that air rises, actually not simple air, but air mass rises up is when two winds meet. For example, if you are familiar with the easterly, so wind is coming from the north, and then wind is coming from the south. They come together. When that happens, they rise up together. And when normally the wind coming from the ocean side, they have moisture, so that gives you rainfall. From the dry side, it's drier, so the moist side will give you rain when they rise together. And that is, by the way, what ITCZ is. IZ is when wind is from the north and the south meet and rise up together and form that rainfall belt called intertropical convergence zone. It is convergence because two air masses converging. That's second way so that air can rise up and give you. The third one is what we see here. So in this case, the air mass coming from the left, when it encounters the mountains, hills, high air land areas, it cannot go through the mountain, so it has to rise up. So it's forced to rise. The winds rise, the water condenses, gives you rainfall, and by the time it goes over the mountain, it's already dry because it has already finished its moisture on what we call the wind side. So the left is wind side and the right is what we call the lee side. That's why in certain areas, at the same height, the same mountain, one side could be dry while the other side could be wet, which is what this cartoon is showing. Now, I can also give you another question. So here, at the given level, at the same level, let's say this mountain is 2,000 meters. Let's say at 1,000 meter level, the temperature on the wind side, on the left side, will be higher than the temperature on the lee side, on the right side. The same elevation, temperature will be warmer on the right side than the left side. Why? Why do you think that happened? I think that maybe one thing you can think about. So this is an example from Kenya. So you can see rainfall on the left. So blue shows high rainfall areas. Red and yellow, orange, low rainfall areas for Kenya. On the right is the elevation. And you can see, so the elevation here is the red area. So bluish areas are lowland, blue-green is lowland, red, orange, yellow is highland. You can see that Mount Kenya and that region. Can you see that the rainfall for Kenya is actually on the western side of the mountain range, while the eastern side, I mean, you can see all the way. So you can clearly see the impact of elevation, the impact of orography on rainfall in Kenya. By the way, you can also see this if you look at Ethiopia and other mountainous African countries. Now, okay, so now you can ask questions. So questions not only about these local factors, but the global factors, what we covered yesterday. Anybody has any questions? You can put in the chat or you can raise your hand. I think somebody already raised their hand, but I don't think. If you have any question, could you answer the two questions you? No, that is for you. Ronald wants me to answer my own questions. You should ask those questions. And mesosphere, but not in the stratosphere. What? Yeah, but okay, yeah. I mean, the text is saying, explaining the decrease in temperature with increasing altitude only in the troposphere. Yeah, that's the troposphere where climate happens. So we are talking. That's why we're talking only about climate.
We have a hand from Moluken.
Moluken, go ahead.
Moluken, unmute and speak.
Yes. Thank you a lot. My name is Mulkan Abtamu. I am from Ethiopia, especially in the southern part of Ethiopia, where I have seen a lot of devastating climate change effects. And I want to ask some question. I mean, I have some question for doctor, and that is, especially you have seen the effect of climate change in Africa, especially in Ethiopia. And what are you doing? What are you doing related to these things? The awareness is really less than other African countries here. And my first question is, have you think about that? So doing something, changing the policy or changing the awareness or influencing the government related to this climatic change? This is my first question. And the second thing is, when I was at the university, I have asked my environmental physics student, I mean my environmental physics teacher who is from India, and he told me that there is nothing here in Ethiopia to do with environmental areas. So I think there is less attention given to climate area or environmental area in Ethiopia. And what are you doing on these things? And could you explain this for me? Thank you.
Yeah, that's a lot of question. In terms of awareness raising, this is what we are doing. This is what Growth Forum is doing, right? I mean, providing climate basics. Because there's no way myself or Growth Forum can reach every corner of Africa. I think the best we can do is to make you, the professors, aware of share what we know, and then it's up to you to share that with others. But also, I'm not sure Ethiopia is the only place where the awareness is low. I mean, in many parts of Africa, it's still the same. Of course, only your area, but there are many people can say about the same thing. But anyway, this is not about.
I think they are better than us. I think I know that.
Well, I mean, we don't agree. There are other people who might be shaking their heads now. But anyway,
Yes,
so
yeah.
outside. So our questions, let's limit our questions to the basic concept. Otherwise, we will be here the whole day if you want to answer those questions. Any other question related to the subject matter? No? Okay, let me see if anybody's raising their hand. I don't see. Okay. No. Let me see, maybe in the text account. So Ayala says Molukan's concern is even more global. Sisu Zakari says everything is clear for him. Okay. Okay, what's the difference? This is a good question. What's the difference between rainfall and precipitation? Can anybody help me out? Gabriel Cross is asking what's the difference between rainfall and precipitation. Anybody? You can just speak if you have the answer. By the way, I didn't go to the question and answer part. Okay, what do I have? Oh, wow, everything is clear. How does the amount of incoming solar energy correlate with local rainfall patterns? That's a very good question. Anyway, the difference between rainfall is only the liquid because precipitation has different forms, right? It could be rain, liquid. It could be snow. It could be ice, right? In grapple format, right? So precipitation covers all those, but rainfall is only the liquid form of hydrometeor falling down. So that's why. In terms of how the amount of incoming solar, so that's the one of the global factors. Remember, I said yesterday I showed these graphics here. This one, this movement is following the energy. It's moving up and down. This is the rainfall belt. You can see those numbers are rainfall amounts, total annual rainfall amounts. So you can see for each month, they move up and down because they are kind of following the sun, which means they are following the energy. Yeah, because remember I said if there's no energy, there's no nothing. So the whole thing is based on energy, surface heating and associated. For example, I said you need moisture for rainfall. Moisture has to come from the ocean, but it doesn't come just like that. It has to be the water has to evaporate to become a moisture. For evaporation, you need energy. That energy comes from the sun. So, and then the winds go either from high pressure to low pressure. That also depends on the energy. So anyway, everything is related to the energy in a global sense. But that doesn't mean, remember what I said, that doesn't mean areas receiving the same amount of energy may have totally different amount of rainfall because of what the factors that I just explained. These local factors. Okay, any other question? Let me see if there's any question in the question part. There's 5. So I think we will come. So drought has nothing to do with Tasfai is asking post-war drought. It's common observation in our case. Can you justify it to us in relation to the factors affecting? So I think this is in a sense a good one for our next section. So I think this first question is, okay, remember the global factors, they are fixed. They are always fixed. The amount of energy coming from the sun for a given location is almost same every year round. The mountains don't move, don't change, or even the land water proximity wouldn't change. But the rainfall coming to Kenya, Ethiopia, or Senegal will change from year to year. So the first question is, can we explain those year-to-year changes, one year being a drought and another year being a flood? Can that be explained in terms of the global or local factors? That's what Tesfaye is asking, right, Tesfaye? Anybody want to answer, Tesfaye? I think anyway, this is a good question. So anyway, we'll come to that. So if the global factors are not changing, the local factors sometimes might change, I mean, not significantly. But some of the local factors, come on. Here, I mean, the topography wouldn't change, but the albedo, the land cover might change, the vegetation might change. That might maybe might change, might moderate the climate, but not big enough to result in a drought one year and flooding in another year. That's fair. I think we will come to that when we talk about climate variability. Let me see if any other question before I go to the next question. So I'm looking at the question sections. Can we do climate change impact auditing for national level by considering balancing effort done by the government? Yeah, we do that could be a 4-day training course by itself. So that is very wide and very broad, I mean. Okay. So I don't see any other questions. So not that less. Let me see one last time in the comment part. So if you have question, can you please let's our interaction in the comments, forget the question and answer session, just stick to the comment section, the comment box, because backend folder doesn't make. Where can we see climate information for different countries? That's different, okay. Yeah. So you can ask that question when you talk about later on data and climate, which might affect the pattern, including local factors. Yes, of course. I was to talk about the man-made rainfall. Man-made rainfall? What's the man-made rainfall? In Tizar, what's the man-made rainfall? Is there a man-made rainfall? Cloud seeding, okay. So, I mean, what is cloud seeding? So remember when I said, so when vapor, moist air rises, it cools down. And when it cools down, it creates results in rain droplet, not in water droplets, very small, tiny water droplets. Those tiny water droplets cannot come to the surface. They are very small. So they have to come together through the process called coalescence. They have to come together. To come together, they need what we call condensation nuclei. So they have to have like some small particles in the air. By the way, if the air is like 100% pure, the atmosphere is 100% pure, there won't be any rainfall, even if you have the moisture and everything. If you don't have those tiny things, what we call condensation nuclei, rainfall will not happen. You will just condense into cloud. It just happens, becomes cloud and then disappear. So what cloud seeding does is it injects those particles into the cloud. it injects those condensation particles so that it helps those small droplets coalesce into big ones and provide rainfall. I mean, there are more details. That is a more general concept how cloud seeding. But so even the word seeding means what? They are seeding into something. And that seeding is those small particles. Normally something, for example, like something salt type things that will be able to collect water droplet, no, cloud droplet into rain. What does mean globe is boiling as in okay, it's not boiling. Okay, membrane. So that's what's membrane for artificial cloud seeding. Yeah, it's artificial because we are the ones adding stuff into the cloud. That's why. Okay, that's different. Okay, there are some each questions coming up, but now we don't have time to cover all of those. So now let's go to the next one. Wow, I'm spending a lot of time, I think. We've done this, we've done this, we've done this, we've done this. So now I want to have a little look at so we looked at global local factors, but these factors, when rainfall forms because of these factors, there are what we call synoptic features that help. It is some kind of a process that helps for number one, for moisture to go from one place to another. Remember I said moisture has to be transported. How can moisture be transported from one place to why is it transported? So that's when we need to talk about this pressure idea, high pressure, low pressure. So first is what is a pressure? Pressure is simply a weight. Pressure means a weight, the weight of the air above your head. Okay. So if pressure is the air above your head, as you go up, would the pressure decrease or increase? Because it will decrease, because as you go up, the amount of air above you will decrease, which means the weight will decrease. Okay, so that's why when in a plane they say it is pressurized, because they are if the plane is not pressurized at that level, there's not enough oxygen, there's not enough pressure. It's very low pressure. Okay, you might even explode. Anyway, so pressure is, again, just think of a weight of air above us. That is it. So there are areas where there is a lot of air or a lot of pressure, a lot of air mass above you. There are areas where are low. For example, if a surface hits, remember, if a surface hits, the air on the surface will become lighter and it will start moving up, start ascending. Because ascending up, at the surface, it creates low pressure area. There are areas where air will be descending down, so a lot of air coming down, that creates high pressure area. Like I said the other day, things go in nature go from high pressure or to low pressure. So the winds, if you have a high mass of air in one place and low mass of air in another place, the wind will try to balance it by blowing from the high pressure area to the low pressure area. As we will see later, so if you want to have a moisture to come to your location, number one, there should be high pressure over the ocean so that the winds come from that, number one. Number two, there should be a low pressure over your area so that the wind is coming from the high area over the ocean will come to the low area pressure area in your area. So anyway, that is a general. You can see the arrows here showing the wind direction. So if you see like the upper level, what happens on the ground and what happens at the upper level for low and high pressure areas. So the first one, you can see low pressure area. That's where air will come to converge. And when air converges at one place, it has to rise. That area will be cloud. That's where rainfall forms, assuming that the rising air has moisture in it. For high pressure area, it's the opposite. That's where the air will be descending, cold air descending down. So that, and as it descends down, it brings a lot of air mass weight with it, and that has to now diverge out, and that is now what creates dryness, but actually, like I said, it will be a moisture source. So assuming you understand what low pressures and high pressures do, let's look at what we have on Africa or and around Africa during the two extreme seasons, January, which is winter in northern hemisphere, and summer in southern, July, August, which is the opposite. So in January, you can see the ITZ is way down, but you can see high pressure area over the Atlantic Ocean. Okay, so and you can see the wind is as they move around the thing. Some of the wind is come to part of Africa here. There's another high pressure area over the Indian Ocean, and there are low pressure areas on the continent. Here you can see over the Sahara area, high pressure area. So you can see the ITZ is where wind is coming from the high pressure area in the down here in the Atlantic, converge with wind is coming from high pressure area over the Sahara area. So dry air coming from the north, with moist coming from the north, they converge. That convergence forms the ITZ. This is in July. Now ITZ is all the way up here. So now actually you can see over Sahara is actually a low pressure area now, most of it. So that the wind can go all the way up here. So that's what the rainfall forms up here instead of down here. Okay. And if you want to see this in a more simplistic way, so again, you can see the ITZ and the winds from south and north for the different seasons. And if you want to see it more clearly, this is your ITZ. Now the ICCZ, it is the difference between the location ICZ in the winter and summer doesn't change much over the coast of West Africa. You can see that, right? ICZ is almost around the same location. It's only slight change over Western Africa between January and July. While over the Southern Africa, it can go to extreme here, and then even continental part of Africa, you can see it goes all the way to South Africa, like Tropic of Capricorn, and then all the way up to Cancer here. Why is that? Why the movement? Very high over the land area, but not that much over the ocean. That's my third question that you can think about. So this is just to show you globally how the ICZ moves up and down, and to see what happens over the Western Africa. So how much it changes from season to season. You can see West Africa's part still hanging almost around the same area. It does move, but you see what's happening now? Compare the other part. I mean, this is of course more a kind of a generalization, but you can see how Z is moving, and you can see over most of the water bodies, including the Indian Ocean, is not the same. The movement over the land and over the water body is not the same. And the question is why that happening? So now to summarize what we have said so far. So we said we define climate as steady, like fixed in place. Of course, it might change. So there are for the local climate, it depends on two factors: the global and the local one. And we said global energy, seasonality, land sea distribution. The local ones, what are listed here, but also climate might vary over time because of these different factors. This is just a summary for you. Any question about this last part? Not the whole thing, but this last part. Anyone to ask question about the last part? These are pressure systems, at Z movement, that kind of thing. Any question? You can either raise your hand or write in the comment section. So that's a very good question. So Joanna is asking why Namibia is a semi-arid country. Again, if you see, it's mostly under high pressure system. Many places, the dry part, they are mostly under a high pressure system. Could you please show that summary again? Why? Shadia is asking for the summary again. And Sarfia, can you please move to the last slide? Okay. This one? Okay, okay. So I'm looking at the chat. I might, but so David, please let me know. Let me look at the comment section, and you can look if somebody is raising their hands. How the high pressure occurs in continents compared to the it's the same thing. High pressure areas where air is descending. Whereas Kenya, the arid areas always receive very strong rainfall, but at the time there is a total drought kind. But I don't know if it's something Meshach. Um, so there are different types of rainfall. There are this what we call convective rainfalls. There's land surface heating and moisture rising up. Normally if uh, there is enough moisture, that kind of what we call convective clouds, convective rain, that can lead to very heavy rain, but very short duration normally. But when convergence areas like at ZZ, they cover wider area and the rainfall lasts longer. While convective rains, this local bubbling up, they can be very short-lived but heavy rainfall, if that's the question. Why also in arid areas we experience because it's high flooding because the rainfall comes at one time. Like I said, it's powering at one very short period. If you have the same rainfall amount spread over the day, there wouldn't be flooding. But if one heavy rainfall falls within a few minutes, even if it is not much total rainfall, but the intensity, that's what matters. How much rain per minute, that matters. Okay, I think another question is about the fog issues. So I think in many cases, fog is when you have the moisture, right? You have a lot of moisture, but the air is not able to rise because it has to rise and cool down to become a rain. But if there is something like if you have a lot of moisture, but still there's some sort of a high pressure area in that region, in that area, then that moisture, there is a lot of moisture, so it can condense to some level, like tiny, because the fog is like what, tiny, very tiny droplets. They cannot form into a rainfall because they're too tiny. They need to go up, condense, or maybe there is no enough condense. So that's one reason why it's forms. There is also something called inversion, but I don't want to go into that. Somebody talking about forecasting. Okay. I think enough of the questions. So before we go into the break, there are some discussion questions here. So I will leave this to you to think about these questions. We have another one, a third one, yeah. Fourth one. Those are discussion questions. The first one is consider a rural area. I think I already talked about this, with agricultural land use pattern and a large coastal city. So agricultural land versus a city on the coast. So it says, if you have a friend, discuss with your friend, this is a discussion, how the different land use would affect daily temperature. What the difference between the temperature on the farm and the temperature on the coast, and what brings the difference? If there are differences, what are the causes of the differences? That's the question. Number two, I think we also mentioned this yesterday. We're good to think about. What are some of the implications, right, of the fact that it is Earth's surface that heats the air instead of incoming solar energy? This also answers one of the three questions I asked you. Remember, if you remember the question, this is the answer, but in the form of a question. The question says here, what are some of the implications of the fact that it is Earth's surface, okay, not the sun, Earth's surface that heats the air instead of the incoming solar energy? What is the implication? Again, I raised one already in the form of question, but yesterday we also talked about one of the implications in terms of summer temperature in Europe and America. So I think you can think about that. Was there anything about how precipitation forms or the relationship between rising air, rainfall, temperature, and that surprised you? Whatever I told you about moisture rising and forming rainfall, that kind of thing. Were you surprised by anything? Maybe not. Maybe you can discuss among yourselves. I mean, normally, if you have time, this would be group discussion in a classroom. So you can do it as if you are giving the students. This will be a good. This question will be good for discussion in the classroom. Again, another one is just asking you. The fourth one is asking you what is the impact of orography. I mean, geography in general on the climate. So I think now we are done with this part. David, I think now it is time to implement that survey. David, can you hear me?
Yes, the survey is online. It is on the screens.
So there are three questions you have to answer. You can see the poll now. How clear and easy to follow the presentation? So the first question is asking about the presentation, the slides. about the the visual thing I used. It's asking you how clear is it, the maps, the graphs, whatever used, how clear and unclear they are. Okay. So about 40 plus 50, okay, 80, 90% are clear to very clear. Sorry about for those people who was very unclear. 5% is very unclear for those. Let's see who is raising their hand in the meantime. Toma, no, Tashoma, you want to say something? You can unmute yourself and say, talk, Tashoma. No? Change your mind? Okay. So we have, well, people are, everybody see the poll questions? Because I see only 130 of 200 something people are responding. So which means only 60 something percent responded. Okay, but anyway, it's not bad. Okay, let's go next question now.
You can scroll down. They have been responding to all the questions.
Oh, I see. Okay.
Okay.
Second question, how would you rate the difficulty level of this is about the subject, the concept itself. How difficult is it? So many people think it is moderate. Okay. Couple of people think it's difficult, very easy. So I think moderate is okay, the difficulty level for that one. The last one, how easy was it to understand? That's about me. The third one is about me. It's asking you how easy it is to understand me. Am I able to explain the concepts? That's the question about them. So the first one is about the presentation itself, slides. Second one is about the content. And third one is about the presenter. So we will do this after each section to see what so I think from what I see, it's not bad. So here is what 50 plus 75% in easy to be. They are really very easy to understand. Okay. All right. So I think we're done. While you are doing this, we will take a 15-minute break. So we'll become like after 50 minutes. So my time is 9:06 now. So we'll come 9:20 or an hour after 20. And in the meantime, let me see if I can do this. Not this one. Where was my? Let me see if I can play one of this. In case you want to, somebody yesterday asked it for what? So David, if you can share the result, will be good anyway to see. Come on.
Imagine waking up to a world covered in a blanket of white, with snowflakes falling gently from the sky. This is everyday life for the people who live in the snowiest place on Earth, Aomori City, Japan. Some places in the city have gotten almost 80 feet of snow in a single year. But if this winter wonderland isn't your thing, don't worry. We can jump over to Lemnos, Greece, a beautiful island paradise with warm sunshine and crystal clear waters, where a single snowflake would be a pretty rare sight. It's safe to say Aomori City and Lemnos have pretty different climates. So where in the world would you expect them to be? Maybe Aomori City is somewhere near the frigid poles, while Lemnos is near the equator. Here's the thing. They're both in the temperate climate zone. In fact, they're both the same distance from the equator. And yet, their climates couldn't be more different. Today, we're going to take a closer look at the factors that shape climates and find out what makes Aomori City and Lemnos seem like polar opposites. By the end of this lesson, you'll be able to identify factors that impact a location's climate and explain how these factors combine to create different climates. Let's get started. Climate describes the long-term weather patterns in an area. There are 5 different main climate types: tropical, dry, temperate, continental, and polar. And each of these main climate types brings different weather, like the hot and humid weather of a tropical climate, or the cold and dry weather of a polar climate. But why? What makes different regions of the Earth have different climates? As we know, the Earth is a complex and interconnected system, so climate isn't just caused by one thing. The unique mix of different factors present at any given location are why there are so many different climates. A lot of these factors are tied to where on Earth's surface a location is. For example, latitude is a measure of a location's distance north or south of the equator, and it has a huge impact on a location's climate. But why do you think that is? I'll give you a hint. Think way back to what we learned about the causes of seasons. Then pause the video here and record your thoughts in your guided notes. Remember, the Earth is tilted on its axis, so while the northern hemisphere is getting direct sunlight, the southern hemisphere is getting indirect sunlight, and the other way around. But the equator is always getting direct sunlight, and the poles are really never getting direct sunlight. This is why low latitude areas near the equator have hot climates year-round. As we move away from the equator and toward the poles, the climates gradually get colder for more of the year until we hit the high latitude areas that have cold climates year-round. The shape of the Earth at a location impacts its climate too. Landforms like mountains and valleys change how air masses move around. They can trap humidity and create lots of precipitation, or disrupt air masses and lead to dry climates. Elevation, or the height of an area compared to sea level, also impacts climate. Remember, as we move higher in Earth's atmosphere, the air becomes less dense. Thinner air can hold less heat, and cooler air can hold less humidity. So the higher you go, the colder and drier it usually gets. Continentality plays a role in determining climate too. Continentality is a measure of how a location's climate is impacted by its distance from the sea. Areas near the coast are often cooler and more humid, with more consistent weather throughout the year. On the other hand, inland areas tend to be warmer and drier, with weather patterns that change a lot through the seasons. This also connects to how patterns of prevailing winds in the atmosphere shape the climate. The places the wind travels through before reaching a location can change the air it brings with it. For example, let's look at this map. If the wind was blowing from the south, how would you expect it to change the weather? What if it was blowing from the north? If it was blowing from the south, it would be coming from over the sea. This would move a humid maritime air mass over the coast, likely causing precipitation. But if it was blowing from the north, it would bring the dry continental air mass with it, likely causing clear skies and big temperature changes. And the movement of the oceans themselves influences the climate too. Ocean currents help circulate heat around the Earth. Just like global wind patterns, ocean currents tend to move warm water from around the equator towards the poles and move cold water from the poles towards the equator. This helps to regulate the temperature of coastal regions. Now, let's put this all together to think like meteorologists and see if we can figure out why Lemnos, Greece, and Aomori City, Japan are so different. They're both at the exact same latitude, so we know that can't be it. They're also both coastal, so their continentality can't be it either. Let's look at the factors that make them different. Most of Lemnos has a low elevation above sea level. It has a couple mountains, but none are very tall. On the other hand, Aomori City sits beside a nearby mountain range with some peaks that reach over 5,000 feet. How do you think this difference in elevation could be impacting their climates? Pause the video here and record your thoughts in your guided notes. Air tends to cool at higher elevations, so it makes sense that Aomori City would be much colder than Lemnos. We're starting to figure it out. But the thing is, higher elevations usually have lower humidity too. So why is Lemnos dry, but Aomori City is snowy? Aomori City receives prevailing northwesterly winds that blow in cold air from over the sea. Cold air plus lots of humidity? Sounds like a perfect recipe for lots of precipitation and clouds by the time those winds reach Japan. In fact, those prevailing winds are why Japan is the snowiest country on Earth. On the other hand, Lemnos often receives prevailing northeasterly winds, which blow from continental Europe. Since they're coming from an area farther from the sea, they carry little humidity, which explains the dry climate. Even though Lemnos and Aomori City share some characteristics like their latitude and their continentality, the combination of all these other factors results in them having significantly different climates. In our interconnected Earth system, just one tiny change in the atmosphere or on the surface can have some pretty huge impacts. So let's review what we learned today. You now know that the climates on Earth are impacted by many factors, including latitude, topography, elevation, continentality, prevailing winds, and ocean currents, and that each of these factors can combine in different ways to create many unique climates. Be sure to complete the questions and extension activities that go with this lesson to practice thinking about climate like a meteor.
Okay, can I assume everybody is back? Were you guys able to watch the video or it was just for me? Were you able to follow the video? Anybody? People went home or what up?
No, they are typing yes, yes, yes in the chat.
So for those people who missed some concept, I think the video covers it nicely, slowly, not fast like me. So I think that video brought everything we said together. It added one more thing I didn't mention, the ocean currents, but that is okay. So I have two comments here. One from Stanley, which is a good point, I think. Personally, this course is very important. Perhaps in the near future, you might think about making this a self-paced course where the material could be expanded, including more materials, to include more aspects on climate change. So Stanley, this is exactly what Reform is going to do. Right, David? That's the whole idea, no? David, Reform, anybody?
Yes, that is what is going to be done.
Okay. So Stanley, rest assured, that is what I think is the whole idea is to put this online, but Reform thought it would be good to provide some like basic introductory presentation before putting it online. I think that's the idea. Can we get presentation? We will get the presentation. I'm not sure if there's any recording. This is GUI. Thank you for the presentation. It was really simple and precise. I don't know what precise means, but okay. I'm a student in physical geography with an agrometeorology option, and I really appreciate this initiative. Unfortunately, I don't have very good level of English, but I can follow you. That's very important, GUI, the fact that you follow. That will be great. Some people of okay, yes, okay. All right. Yeah, so Turi, yes, come on. Yeah, the video explained well, but you explained better too. Okay, thank you. Because you have example from countries we are familiar. Okay, that makes sense, right? Instead of somewhere in Japan or whatever, I think focusing on the countries we know might have. Yeah, I mean the video is from YouTube. So for those people who want, I can share the YouTube link if you want for that video. So I mean, I think the document will come maybe sometime. I have to clean up everything and share it with Reform. Then it will send it to you. So I need some time to reorganize things because I'm also improving things based on. Okay. Now, so let's go to the case climate variability. Okay. Climate variability is very important because a couple of people ask, remember, why is it raining one season and why it is not raining another season? Like I said earlier, the global factors are constant. They don't change from year to year, mostly. Even the local factors don't change from year to year. Mount Kenya will be Mount Kenya, I don't know, for thousands of years. So we didn't change. Many of the oceans, Lake Victoria, we don't expect to change. But still, you will see there in certain different parts of Africa, certainly last year, for example, this year, most of this year actually, been flooding in many parts of Africa. The other years, drought, especially in Eastern Africa, Horn of Africa. Why? If we say the global factors don't change, the local factors don't change, what is happening? That's what we try to address in this presentation. So we'll go into the two main factors. Actually, it's only one, but two of the main factors. So this is the first thing, is just to repeat what I said before. As if the sea surface plays a significant role on the climate, especially on climate variability. We'll come to why. But assuming like if a cold and warm part of the ocean, I mean, this is showing you, like say the warm part, and then it cools this way and cold that way. The whole idea is what I said before, because this is warm, hot, the energy evaporates the water, and that water ascends because this is less, it's buoyant, right? It's lighter and buoyant, it rises. At ascends, it becomes a cloud, and that cloud becomes a rain. So this is the factor. But in many cases, this rainfall might not form here. The moisture might rise, and the wind might take this moisture somewhere else, and that can lead to rainfall. Okay. Might give rainfall somewhere else. So what is the issue now? So one major source of what we call interannual variability. So there are many types of variability. There are day-to-day variability, month-to-month variability, decadal variability, or even 100-year, 1,000-year, different kind of variability. But the one we are dealing with here, the one we are concerned about here, is the interannual. Interannual means from year to year variability. That some of you asked it earlier. And like I said, this one of the major responsible factors is what we call El Niño Southern Oscillation, in short, or abbreviation is ENSO. And this is what something happened over the oceans. So it is something happening on the ocean, and with interaction, of course, with the atmosphere. Otherwise, if the ocean phenomenon doesn't interact with the atmosphere, then wouldn't affect the climate anyway. So this is because of something happening on the ocean and that interacting with the atmosphere. So one component we call El Niño. Okay, El Niño, that is the ocean component. Okay, it is the ocean component, but actually, I mean, we say El Niño, but La Nina, both El Niño and the La Nina are the ocean component. What happens at the ocean, on the ocean, we'll look at it later. The southern oscillation part, which is the oscillation part, represents the atmospheric response to what happens on the ocean. So that's why it's called El Niño Southern Oscillation. The oscillation is this change because of what happens on the ocean surface. There are oscillation. Oscillation means changes from year to year in terms of the impact on the climate, impact in the atmosphere. So we have two events on the ocean. The El Niño, when the temperature is warmer than normal, which means when the anomaly we talked about yesterday is when the anomaly is positive. That is El Niño over the Pacific. And La Nina is the opposite, when the sea surface temperature over a specific location is above expected, or where the anomaly is negative. For people who speak Spanish or even Portuguese, Nino, El Niño, Niño is a boy, and Niña is a girl. So, I mean, there are historic reasons why, but something to do with this phenomena happens near Peru, in Latin America, and so Nino has something to do with Preston, that maybe I don't know what the La Nina part is. So these are those phenomena. So if you see this is So what normally happens, this is South America, okay? And this is Peru is around here. This is Central, this is Caribbean actually. And so this is the Pacific Ocean all the way from, this is the what we call the Eastern Pacific, and this is called the Western Pacific. Africa is somewhere here. I think this must be Australia. South Africa must be somewhere. Okay, so this ocean plays a huge role in this what we call interarmal. Normally, this part is a little bit warm. If you look around here, just this coast here, the Peru coast, it is normally it's a little bit cold. So because it's cold, it's warm here. When air rises here, warm because the pressure will be less here. So wind will flow from east to west. This is the normal. So it raise up and ascends here, giving rainfall, and descends down here, resulting in dry condition. What we call the average normal condition. But when it's El Nino, is El Nino. Now you see this part, which was blue, now is orange red, which means is now temperature has increased. Okay, so this area has become now warmer than what we see here. When that happens, so this wind is weak. So instead of, because here the wind is very strong, you can see like the arrows is showing you how strong the wind is. But here is a very weak wind here. So instead of the rainfall ascending here, actually now it moves. Right. So certain areas which used to get rainfall will have less rainfall. Areas which didn't have rainfall now will have more. I mean, this is a cartoon, by the way, so you don't take it literally. But this will happen around the world. So this effect, this will have what we call a ripple effect around the world, around the globe, and especially within the tropics. And it has even extra tropics. It will change the rainfall and rainfall and temperature patterns around the world. The La Nina is the opposite. Now you can see during the La Nina, it's even colder than the neutral. So see, here it is colder, and even this wind is now even stronger than the neutral, the one we see here. And because of that, the hot water is pushed all the way toward the west. And so now again, the rain belt in this case is shifted to the west, again now shifting the rainfall and temperature patterns in a different direction around the globe. So this is one of the big factors that affects interannual variability, rainfall variability from year to year. Not, I mean, yeah, it is, we say year to year the way we see it, but it could be like 3, 4, 5 years in a row drought, in another 3, 4 years, maybe, I don't know, 2, 3 years flooding, and maybe another 2, 3 years normal. So that's how the cycle goes. So when we say El Nino, so it is, we measure the temperature. Again, you can see the Peru coast, this is South America. So there are different parts of El Nino. You see different box 1, box 2, box 3 here, box 4 here. So normally this box here, the 3.4, which is an intersection of box 4 and 6, is where the temperature measurement is taken. System temperature is taken to not only temperature, but there are all the other parameters that are measured now to see. So when we say above normal, below normal, whatever, it is what is measured here in this box 3.4. So again, the strength is dependent. We'll look later about that. And this measurement, this is what you can get from these measurements. So if you look at this is what we call anomalies, right? This is the difference between the mean and the observation for each year. So the red ones are mostly El Nino years because it is warmer than normal or higher. The index is higher. Blue, the index is lower, which means La Nina years. And if you see, if you any remember, I don't know, 1983, 84, really huge El Nino, where Ethiopia, for example, had devastating drought, even famine. Around 87, another El Nino. I don't know if anybody remembers the 1997 El Nino for Eastern Africa, Kenya, Southern Ethiopia, it had a big impact. So El Nino will come later, but the impact is different over different parts. Even over Kenya, the impact of El Nino during March, April, May is different than the impact of El Nino during OND, October, November, December. And the recent El Nino, if anybody remembers, 2015, 16, East Africa again, big thing. And it's the La Nina, which hit Eastern Africa from 2020 onward. You can see that 2021, even 22, resulting in very dry March, April, May in Eastern Africa during March, April, May. The same led to very good rainfall during June, July, August over Ethiopia. Actually, if I'm allowed to talk politics, this La Nina here helped actually maybe a serious conflict between Ethiopia and Egypt. Because if you remember 2021, 22, that's where Ethiopia was feeling its big dam. And because it was La Nina, there was excess rainfall. There was flooding in Khartoum while Ethiopia was filling the dam. So, I mean, imagine now, if Ethiopia tries to fill the dam during this El Nino, the 2025 El Nino, either Ethiopia would have hard time to fill the dam on time, or would create some conflict with the downstream countries. So I think it was bad for Southern Ethiopia, actually very bad for Southern Ethiopia, the La Nina, but it was very positive. It has positive impact for a northern half of Ethiopia, especially where the Renaissance Dam is located. So El Niños, there are what we call strong La Ninas, strong El Niños, weak La Ninas, weak El Niños. It all depends on these numbers. So you see from -1 to 1, so -1 to 0 is actually 0.5. Otherwise, so between -0.5 to 0.5, negative to plus 0.5, that's called neutral. Okay? Between 0.5 and positive, between negative 0.5, the index, to 0.5, that is neutral. And between -0.12, 0.5 and -1, weak La Nina, up till -1.5, moderate, and then above that strong. The same for El Nino. So that's also how you say this. So if you see the 1997 El Nino, it was what? Really very strong El Nino. 82, 83 El Nino. Can you see that? That was strong El Nino. When is the 2015, 20 something? You can see here also 2015, 2016 El Nino, strong El Nino. La Nina, okay, we don't have the latest one, but I think we can see 2000 La Nina, moderate. I don't see very strong. Maybe it's this one. 1975, 74, very strong. If you see here, it would be maybe because it ends in 20 something. If you have longer, it will. Let me see. Why don't you see? So -2. So this it's almost -2. So -2 is what? -2 is strong, no? So you can see this La Nina was very strong. La Nina is almost up to negative. Another strong La Nina here. Okay. So what is the impact? Over different, you can see, forget the other part, but if focus on Africa. This is like what the impact of El Nino on rainfall. So green means wet. This yellowish is dry. So El Nino is, you can see it is during what, between September and January, anything, September, January, September, January. So which means OND season for Kenya, for example, it is positive. So that's why, like I said, 1997 El Nino was very wet. But same time, during November to March, Southern Africa, and June, July, August, during the northern rainy season from West Africa to Ethiopia, El Nino is very bad because, okay. And La Nina, so this is another thing. So I will show you, this is a map. It's actually, this map shows for Senegal and Ethiopia, the probability of having dry rainfall, the July, August, September being dry during El Nino. So the probability goes from blue 0 to the red 100%. So if you look at the Ethiopia, okay, so this is based on, so this is not a forecast, this is based on historical data. I'll tell you where data comes from, but based on historical data, 30 or 40 years of data, both El Nino and rainfall data. So here it shows for Ethiopia, during June, July, August, the probability of having dry June, July, August, September is really very high for red areas. Southern half, you see that it doesn't matter much because that's not rainy season. Western part of Western Ethiopia, even though it's rainy season, El Nino doesn't seem El Nino to affect. So it is mostly northeastern part of Ethiopia and what we call the Rift Valley that is affected by El Nino. And the people living in Ethiopia should have some idea about this. Senegal, it's mostly what, about 50%, maybe 40-50% depending. It does, El Nino does affect it, I don't know, 40-60%, some area to 70-80%. But there are also parts of Senegal which doesn't care about El Nino as well. So, but this is available online, what we call MapROM. We'll talk about that maybe tomorrow. Impact of La Nina on rainfall, again, it is the opposite. So you can see November to March being dry during La Nina. Over the Kenya, southern Ethiopia side. That's what happened from 2020 to 2022. But it's good for Southern Africa. It's for during November to April, good for the monsoon, the summer monsoon region all the way from Senegal to Ethiopia during June, July. That's why I told you where Ethiopia had so much rainfall during 2020, I think 2022. Okay. So this is another map showing probability of dry La Nina during March, April, May season during La Nina. You can see most of Eastern Africa, I think on this map, being in the yellow and red means high probability of being dry during La Nina for the March, April, May season. So the other one is the Indian Ocean dipole. I don't want to go this into detail because it only affects Eastern Africa part. So this affects Ethiopia, Kenya, Somalia, to some level maybe Tanzania. I don't know how much that is. But that depends on the ocean temperature over the Pacific. It switches. The hot and warm switch between different seasons, and they affect the rainfall independent of the ENSO. This is in addition to the ENSO. So sometimes IOD plus ENSO, IOD might moderate or amplify the impact of ENSO, but I don't want to go into detail on this one. Again, you can, so here is where you can measure the IOD west-east, and this is what we have seen before in terms of measuring ENSO. Okay, IOD, this is again the time series of the same index for now that Indian Ocean part. Done now, it's up to you to ask questions. So that is where climate variability comes from. For people who wanted to know why is 1 year dry, another year wet, voila. I hope I have answered your question. If not, you can ask questions now. can raise your hand or in the comment section, in the comment, right, in the chat board, because I cannot switch between the two there. And David can help me with anybody raising their hands.
Yeah, someone has raised the hand called Carol Ndongo. Carol, you can unmute yourself and ask the question.
Somebody's asking for IOD. This one? Yeah, that's IOD. He says La Nina was predicted in La Nina. Didn't happen this year, I'm not sure. Was it predicted? La Nina was said predicted. I think there was some La Nina, no? I don't know. Maybe we can, why not we check? Come on. We can check. I don't know what IRI forecast. By the way, if you want to see the prediction, you can see here. So where is it? This is the seasonal forecast, by the way. Where is the INSO forecast? Come on. Where is the IRI INSO forecast? No. There. Okay. Okay, so these are INSO forecasts. One from IRI, another one from NOAA. So where are we now? October, we are here. This is the forecast. So, I mean, this is what, August, September, October? August, yeah. So yeah, so where is March, April, May? DJF. It's January, February. So January, February, March this year was mostly La Nina, blue. February, March, April, some other La Nina, but and neutral equally. And then March, April, May, mostly neutral. And the forecast for what is this one? Whatever. So it's moving from La Nina years, La Nina phase to more neutral phase. Okay. Oh, I was not looking at the question. Let me see. Okay, well done. Okay. Well, okay, so somebody is asking about attendance leak, David, many times. Okay, what's the difference between La Nina and El Nino? Let's say La Nina is above below normal temperature, and El Nino above normal temperature. The Indian Ocean dipole is, maybe I should explain that one. Yeah, why not? So, this is the Indian Ocean. So this is the location. So this, you see this west, the temperature IOD stands for Indian Ocean dipole. Dipole means dipolar, like two polars. So two polar means what the temperature between west and east part of the ocean, the Indian Ocean. Sometimes the west is warm, the east is cold. Another time it is the opposite. This is what you see here. You see, neutral, this is it. But during what we call positive, the part of the ocean close to Africa will be warm, while the one in the east will be cold. This will create air moving from here to here, and it is good for Eastern Africa, Ethiopia, Kenya, because it will increase rainfall. Other years, now it's switching. Other years, the Eastern Africa side becomes colder, and then on the East Indian Ocean becomes warm. Now the wind is reversed, so it is less rain. It will depress rainfall over eastern part of Africa. That's what this is. Hope I answered your question. Attendance, again, people are complaining about attendance. This is a good question from Sintayo. Why is not western part of Ethiopia influenced by El Nino? And so I'm not sure. I'm just showing the data. So but it could be some local issue there that may not be affected, but I'm not sure. That's a good question. Yes, a lot of times there is combination between ENSO and IOD, many times. That's why sometimes they tell you it is La Nina and it's going to be bad, or it's El Nino is going to be bad, but might not be bad. I remember it many times when the IOD either made ENSO worse or better, depending on its phase. Yeah, definitely they do act together, depending how strong they are. Okay, I think the more info we'll talk more. I have video on more about maybe for tomorrow. I think today we don't have time about El Niño and La Nina. Small video. Well, Francis saying, what is the forecast for the next? I mean, I already showed you, right? The forecast for next season, El Niño, La Nina. They give you probabilities. Maybe I should explain that more for people who want to. I just brushed it, so for people who want to understand that. So this is the ENSO forecast. So you can see that. So this is blue, La Nina, neutral, and red is El Nino. Where are we now? We are in September, right? So we are here, October, November, maybe actually we are here. But you can see the forecast all the way until April, May, June next year. This is the forecast. And this is probability. The y-axis probability. And E, so August, September, October, November, October, November, December, every 6 months overlapping. So you can see the forecast now, this point of observation, until even November, December, January this year, not even until December, January, February, is mostly. So here, for example, 80% La Nina, over 80% La Nina for the November, December, January. About 70-something% again more La Nina, but now the probability of La Nina having it decreases, and at one point actually having the neutral increases, and you can see neutral, and then also the probability of having El Nino coming back maybe sometime next year, but you can also see here, if you don't want to read here, you can get it. So La Nina 38, this is what, this is this one, right? So La Nina is what, 30-something% here. So 38% La Nina, 60-something% neutral, 0 La Nina. And the highest La Nina forecast is 83% in November, December, January, this one here, okay? So this is IRI data library, IRI forecast, but there are two forecasts, by the way. There's IRI forecast and there is the NOAA forecast. I think this one is now mid-September. I think the same thing, but yeah. You can also see the models and the current time series. So anyway, if you're interested in a linear forecast and what's about, you can come to the IRI webpage, which is just I showed you. Okay. Well, let me see any other question. Not too many questions, but just to see. Okay. Well, understandable the difference between, okay, somebody understand. I have a question. Does the phenomena of La Nina induce the phenomena of El Nino? No. I mean, they're the opposite. So it is not, they follow each other. Right? It's a couple of years, La Nina, a couple of years El Nino. So it's not one leading to other. What is the average return period of El Nino? I mean, it depends. I mean, you have to look at the here, no? I mean, instead of asking me, you can look at this curve. So it's not, people say 5 to 7 years. So you can see what, yeah. So El Nino, let's say here El Nino, then El Nino came back here, then sustained. So it's very random, but you can see there is some sort of a cycle, but it's not very something you can say, okay, people say 5 to 7 years, but you can see some, like here, like you had La Nina for 3 continuous years, and here you had El Nino for I don't know how many years continuously. So it's hard to say this many years. Could you present the last slide? Or I did. What is the average return? Okay. Can you please elaborate further between La Nina, which I did, but we'll come back to that with the video, not in the. What could explain why wasted? Okay, that's what I said earlier. So if we have finished, can you on the, so the duration, I don't know if you're not here, the training will continue tomorrow and Friday. Okay, so always the same hours between tomorrow and now, before you forget, will be good, David, will be good to do the, I mean, there are some discussion questions which you can think about. Look at this one. In the meantime, can you do the poll, David, for this one?
No, they already responded to the poll because it's the same questions.
No, but that's for this section. I think we want to ask for each section separately. Or does it work that way?
Okay, it's okay. Let me see. Maybe I duplicate it.
Okay.
I think you can relaunch it.
Yeah, but it will be cumulative. That's
Oh,
the
okay.
problem. Yeah.
Okay.
So that's why I'm seeing. I think let me see whether let me just duplicate it, and then I relaunch. Okay.
Okay, in the meantime, people can ask questions. Because we are done. We are almost 1 minute left. Because we started maybe like 5-10 minutes late. So you can hang around another couple of minutes. Could you please explain again the concept of El Nino and La Nina and their effect related to the rain drought? Which country? Because okay, anyway, so we'll do a video tomorrow during the break and we'll see if you follow it. Okay, this is a good question. So what because it was La Nina, no? Let me see. This is a good question. So how do we explain heavy rainfall in Sudan? This because we had La Nina again, no? Somebody was asking why heavy rain again. I have to go back.
I've launched
That's a
the
good question, huh?
I've launched the poll.
Okay, please respond to that poll. No, what is it? I said in the forecast, no? In the forecast. Somebody asked about Sudan. So what was happening in, you see, in what? June, July, August, no? What is it? It's August, September, but it was mostly neutral and actually it doesn't go back to June, July. But I think it was still La Nina, mostly La Nina and neutral prevailing. That was why we had, not just Sudan, Ethiopia, we had a lot of heavy rainfall over Sudan, over Ethiopia as well. I'm just responding to a question. You already, yes, you respond to that poll, but that, so I'm asking the same poll, the same questions for the different sections to see which section is easier or harder to understand, so that because different section might have different level of difficulty. That's why we are asking the same questions, but for different sections. So Alex wants to, where can we get all this data to predict the La Nina and El Nino? You don't have to predict the La Nina and El Nino. You just go and get the what predicted. Okay, or you meant the one I displayed for Kenya and East Africa, that I will show you on Friday, maybe tomorrow. I can show you tomorrow. But this one, the one I'm on the web page, you have to go to IRI web page or no web page to see the forecast. So heavy rainfall on Sudan, I try to explain. Somebody want to know, explain more how the index is calculated. I think it is not just temperature, by the way, the Nino index, it includes other factors. I can give you a link if you want. Attendance. Okay. Okay, somebody wants to have more from Southern example from South. I mean, I've been using Zambia from Southern Africa. By the way, there is a reason why I'm only using few countries because of the information we have. I will also explain that why tomorrow. Actually, I haven't used much of West Africa. Actually, South Africa, I've been using Zambia. So. Okay, so you can share the result for the survey, David. Would be great. What do we see? So this part again clear. Difficult to tell percent of the people, but otherwise okay. Yeah, because I want to see how people feel about different sections, David. So we'll be doing the same tomorrow, different polls for the different sections.
Okay. No problem. It's okay.
No. All right, everybody. Thank you very much. Hopefully you have captured a couple of things worth your 2 hours. Like I said, I hate teaching remote because I don't see people face. I want to see people faces while I'm doing this, but unfortunately this one is, but still it's better than, right? I mean, for you, it is better than not having the training, so it's okay.
Yeah, yes, Tufa. Hopefully tomorrow we shall also be seeing your face as you teach.
Yeah, well, but I'm trying to save the band. That's why.
But we still
Initially,
want,
when I started, I showed my handsome face actually.
yeah, we still want to see your handsome face even as you continue. in the journey.
Okay.
Yeah, thanks.
Well, you suspect maybe it's somebody else teaching instead of me?
It could be AI.
All right. Anyway, thank you very much and see you tomorrow, same time, everybody.
Okay, thank you very much,
Thank
Dr.
you.
Kifa. Much appreciated.